Chemistry powers today, but courageous chemistry is shaping our tomorrow. It's fueling the hydrogen economy and driving clean energy. It's in our semiconductors and even powers our 5G. It makes bridges stronger and medical equipment safer. Chemistry powers progress and binds us all together. But there's something more that sets us apart. Courageous chemistry.
Welcome to class. In today's lesson, we'll be looking at particulate nature of matter, and in this series we are going to be taking a look at ions, atoms, formulas, and the relative molecular mass, and of course relative atomic mass. Okay, when we talk of particulate nature of matter, we are looking at what matter is made up of. Okay, now you know that matter is made up of discrete particles. These particles can exist as either atoms, it can exist as molecules, it can also exist as ions. Okay, now let's take a look at what atom is. An atom is the smallest particle of an element that can take part in a chemical reaction. We represent an atom with the symbol of the element without adding any numbers to it. All right, take note of it. Now, the atom per se consists of proton, neutrons, and what? Electrons. Take note of that also. Molecule. What is a molecule? Molecule is the smallest particle of a substance that can exist normally or individually and still possess both the physical and chemical properties of that substance. So molecule can be atoms that are grouped together. As you can see there, we have 2 oxygen of atom equals to 1 molecule. Okay, 3 atoms of oxygen equals to 1 molecule of ozone. Is it not? Yes. Molecules can also be group of elements. Okay, for example, H2O is water. What is atomicity? Atomicity simply means the number of atoms in 1 molecule of a substance. For you can see for oxygen now, the atomicity will be number of atoms. There's how many? 2. So atomicity will be what? 2. Or we say it is a diatomic. For ozone, the atomicity will be 3. And we say it is what? Triatomic. Is it not? Yes. So the number of atoms in 1 molecule of the substance gives us the atomicity. Take a look at this following example and tell me the atomicity quickly. Okay. So the first on the list is helium. How many atoms do you see there? 1. So it is monoatomic. For oxygen, how many do you see? 2. Therefore, it is what? Diatomic. For chlorine, how many do you see? 2. It is also what? Diatomic. Finally, for ozone, how many do you see? 3. So it is what? Triatomic. Let's now take a look at ions. What are ions? An ion is any atom or group of atoms which possesses an electric charge. Remember, an electric charge can either be what? Positive or what? Negative. Is it not? Yes. Generally, when elements lose electron, they form positive ions. We call those positive ions cations. While when element or compound gains electron, they form negative ions. We call them anions. Take note. Positive ions, cations, negative ions, anions. Now, these substances either gain or lose electron. Okay, it has nothing to do with their proton. Take note to they either gain or lose what? Electrons. Let's look at Dalton's atomic theory. John Dalton was the first scientist to carry out experiments concerning the atom. The discovery of his experiment, or the result of his experiment, has then made him to propose some theories, which we now call Dalton's atomic theory. And one of the theories says that all elements are made up of small indivisible particles called atom. Now, by indivisible, we mean it cannot be divided, is it not? Yes. The second theory proposed is that atoms are neither created nor destroyed, but can change from one form to another. And then the third theory also proposes atoms of the same element are alike in every aspect and differ from atoms of other elements. Okay? And he also proposed a fourth theory known as when atoms combine with other atoms, they do so in simple ratio. And finally, he gave the last theory, which states that all chemical change result from the addition of atom or the separation of what atom. Now, after many years, scientists discovered that some of these theories were not true. Okay, that led modern chemists or scientists to now change or modify some of these Dalton's atomic theory. Okay, so because the theory could not stand test of time, remember from our knowledge of scientific method, the theory could not stand test of time. Dalton's atomic theory had to be what? Modified. When I say modify, I mean it had to be what? Adjusted so that it can fit into modern what? Discovery. One of these theories that is modified is the first one that says all elements are made up of small indivisible particles called atom. Of course, you now know that the atom is not indivisible. Instead, it is further divided into three subatomic particles, which are what? Neutron, proton, and what? Electron. And of course, we know that the proton and the neutron is found in the nucleus of the what? Atom, while the electron revolve around the what? Nucleus of the atom. So we have to modify that one. The second one also that says that atom are neither created nor destroyed is partially true for a type of reaction we call chemical reaction. But there's another type of reaction we call nuclear reaction. Is it not? Something you did call radioactivity in GS3. Now, in nuclear reaction, you will see a heavy nucleus. We break down into two or more less heavier nucleus. This reaction violates Dalton's atomic theory that says atom can neither be created nor destroyed. So for chemical reactions or ordinary chemical reactions, this Dalton's atomic theory holds true. But for nuclear reaction, it does not hold true. Do you get it now? Yes, I believe you understand what I'm saying. So the other one that says atoms of the same element are alike in all aspects but differ from atoms of all other elements is not actually true because of a phenomenon known as isotopy. Isotopy is a phenomenon whereby two or more forms of an element exist having the same atomic number but different mass number. The difference in the mass number is due to the number of neutrons present in the nucleus. An example of element that exhibit isotopy is hydrogen. In fact, most elements exhibit isotopy, okay? In this case, now we'll say there are three isotopes of hydrogen. All of them have the same atomic number, but they have different mass number, as you can see. All right, let's proceed. The Dalton's atomic theory that states that when atoms combine with other atoms, they do so in simple ratio. This theory still holds true for most chemical reactions, okay? However, there are certain reactions in which you have large molecules combining together, okay? For example, you have carbon. Carbon has a very unique ability to form large molecules, okay? Now pay attention and learn more about relative atomic mass, relative molecular mass, and percentage composition by mass.
Remember from previous videos, we can find the mass number of any element by looking in the top left corner of its nucleus symbol. And this tells us the number of protons plus the number of neutrons in its nucleus. Sometimes though, the nucleus symbols will show the relative atomic mass instead, which is the average mass of all the isotopes of that element, and is denoted with Ar. So whereas particular chlorine atoms could have mass numbers of 35 or 37, chlorine as an element has a relative atomic mass of 35.5, because that's the average mass of these two isotopes when we consider how common each one is. But what if we want to find the average mass of an entire compound, which will obviously have more than one type of element in? Well, that would be the relative formula mass, which we always write as Mr. To find it, all we do is add together the relative atomic masses of all the atoms in that compound's molecular formula. So if we took magnesium chloride, which has the molecular formula MgCl2, we'd have one magnesium, which has a relative atomic mass of 24, and two chlorines, which each have an Ar of 35.5. So we'd do 24 plus 35.5 times 2, giving us a relative formula mass of 95. Or for sulfuric acid, which is H2SO4, we have 2 hydrogens, 1 sulfur, and 4 oxygens. So 2 times 1 plus 1 times 32 plus 4 times 16, which gives us a total of 98. So the MR is 98. You could also be asked to calculate the percentage mass of a particular element in a compound. For example, we could find the percentage mass of sulfur in sulfuric acid. For this, we do the AR of the element we're looking for, times the number of atoms of that element, divided by the MR of the compound. And then we multiply it all by 100 to turn it into a percentage. So here we would do 32, which is the AR of sulfur, times 1, because there's only 1 atom of sulfur in sulfuric acid, divided by 98, as that was the compound's relative formula mass that we found a minute ago. This gives us 0.327, which we then times by 100, giving us our answer of 32.7%. Before we finish, let's find the percentage mass of oxygen in calcium hydroxide, which has the formula CaOH2. The first thing to do is to recall our formula and check the periodic table to find the relative atomic mass of each element. So 40 for calcium, 16 for oxygen, and 1 for hydrogen. So for the top of our equation, we need to do 16 times 2, because we have 2 oxygen atoms. Remember, the 2 after the brackets applies to both the oxygen and the hydrogen. Then to work out the MR, we do 40 for calcium, plus 2 times 16 for oxygen, and 2 times 1 for hydrogen. So if we simplify it, we get 32 divided by 74, which we times by 100 to give us 43.2%.
If we consider carbon, its relative atomic mass is very close to 12 atomic mass units. This is because, in nature, 99 atoms out of 100 atoms of a carbon sample are carbon-12 isotopes. Another way of saying this is that carbon-12 has a 99% isotopic abundance. However, not all relative atomic masses of elements are weighted in this way. Chlorine, for instance, exists as 2 isotopes, chlorine-35 and chlorine-37. How many protons and neutrons do you think each chlorine isotope has? Remember, the mass number for an isotope is equal to the number of protons it has plus the number of neutrons. Pause and select from one of the following options. Use the chemical symbols to help you work this out. Both chlorine-35 and chlorine-37 have 17 protons, but the chlorine-35 isotope has 18 neutrons, whereas the chlorine-37 isotope has 20 neutrons. The answer was A. Did you get it right? In nature, out of 100 atoms of chlorine sample, 75 of those atoms are chlorine-35 isotopes, and 25 of those atoms are chlorine-37 isotopes. For you to be able to work out the relative atomic mass for chlorine, you have to multiply the mass number of the isotopes with its abundance, percentage, and add these products together. This gives the total mass number of the isotopes. Using this data, can you calculate the total mass of chlorine isotopes using their abundance and mass numbers? Pause, think, choose, and continue when you're ready. The answer is B. You have to multiply a 75% abundance of the chlorine-35 isotope by its mass number 35. You then have to multiply a 25% abundance of the chlorine isotope by its mass number 37. When added together, this gives a total of 3,550. The final step in calculating the relative atomic mass is to divide your answer by 100. This is because the abundances are given as percentages. This means chlorine has a relative atomic mass of 35.5. Here's a challenge. From the following data, calculate the relative atomic mass of uranium. Pause and continue when ready. Make sure you write your working out down as you do the calculation. The correct answer and working out is displayed on the screen. Remember, you then have to divide this value by 100. That gave you 237.99. Did you get it right? In summary, The relative atomic mass is the average weighted mass for the isotopes of a particular element. To calculate this, you need to multiply the relative abundances by the mass number of the isotope, add these products together for each isotope, and then divide the total by 100. And that's how you calculate the relative atomic mass of any element from its isotopes in the periodic table.